Okay, great. Hi everyone. My name is Andrew from Nanyang Technological University of Singapore, and I'll be talking about my work done during this summer together with Fire. It's titled "Learning to Predict Dialog Breakdown from Turn Transition Probabilities in Embedded Spaces." So this is my overview. I'll be talking about three main things: the background, the training, and then finally the result. Okay, so first off, what is dialog breakdown? Dialog breakdown is defined here. A dialog breakdown has happened if users cannot proceed with a conversation in a given dialog context. Sorry, I think. Yeah. Dialog breakdown is one of the many forms of dialog evaluation, and basically it encompasses different dimensions such as coherence, consistency, and common sense. I think you are clicking on the.
Yeah, I had to stop my video, but the
Okay.
clicking is a bit confused between the control and the content. I'm not going to touch it anymore. Go for it.
I can't. Okay, it's working now. Okay, right. So I was saying dialogue breakdown is one of the many forms of dialogue evaluation, and it encompasses different dimensions like coherence, consistency, and common sense. In this work, we are going to focus on the final grain, turn level dialogue evaluation, and not dialogue evaluation at the dialogue level. So why is dialogue breakdown so important? We need to be able to determine how good a dialogue system performs without constantly relying on human annotation. Currently, it's still a relatively unsolved problem. DBT4 held in 2019 only had an F1 score of around 0.469. So currently, dialogue breakdown detectors are not very precise or sensitive. Okay, so over here, I will show some exploratory work before I go into the bulk of my research. So we want to show the prediction of utterances in 2D spaces. So what we did is that we compute TF-IDF features, and then we perform TSNE to reduce the dimensionality to 2D. So the dialogue in this example is taken from a movie DIG dataset, which is a dataset containing dialogue from movie. So I'm going to play the video over here. Hopefully, I'll increase the speed by a bit. Okay, so the general idea of this video is that, let me exit. Alex, can you help me to exit the video?
Okay, let me.
Sorry about that.
Okay, let's see. Let me stop and restart. So, actually, do you have control?
Right now, no, I think.
Okay, so the problem is all the. Let me. Okay, so I think what we have is these. Let's go from this.
Okay, could you go back to the slide with the video?
Okay.
Yeah, sorry, yeah. Sorry about that. So the point of video was to show that there are areas for which the utterances often bound to. So what if we could define a region for which it's more likely or more unlikely for an utterance to bound to? Could we define good or bad region that we can use to our advantage? Okay, so we are going to try taking on an unsupervised approach toward this problem. So what we do is that we perform k-mean clustering on features to try to separate them into distinct regions. So the obvious benefit is that we don't need any kind of annotation to perform clustering, but we do want to use good dialogue, such as human-to-human dialogue, where conversations are coherent without any dialogue breakdown. However, one issue with k-means is that the performance is very reliant on the starting initialization of the cluster. So there's a slight bit of training instability introduced here. Okay, so instead of using TF-IDF, as we showed earlier, we experiment with using contextual embedding as our feature. We have two models over here. On the left is a very popular BERT model. Sorry. On the left is a very popular BERT model. And on the right is another somewhat popular Dialog GPT, which is pre-trained on dialog data. Dialog GPT is an autoregressive decoder, while BERT is an encoder trained on general text data. So we extract this embedding from the second last layer of these two models. And these embeddings are said to encode thematic information about the input, and their dimension can be from 768 all the way to 1600. So this is our training data. We take 5 data sets to compute the embedding: movie DIT, corner movie, personal chat, empathic dialogue, and daily dialogue. These data sets are all human-to-human conversation without any utterances from dialogue system. After filtering, we have around 800K of utterances to use as training data. We then compute k-mean as mentioned earlier. So how can we identify good and bad clusters? So we built on another paper which proposes the fine-grained evaluation of dialogue metric, in short, the FAD metric. So the FAD metric essentially proposes computing the loss of a list of positive and negative follow-up utterances for several qualities. For example, if we want to evaluate on interestingness, we compute the loss of the follow-up utterances. Wow, that's really interesting. However, the FAD metric is a relative score, meaning we would have to calibrate the loss on some system before we evaluate on another one. So I have an example on the right. So this is a pair of speakers. So the first speaker says how is the weather today, and the second speaker replies great. So Dialog GPT will then compute the loss of a series of follow-up utterances. Okay, so these are some examples of the FAD metric. So it's only 2 of the 5 metrics shown over here. So what we do is that we did not use the original FAD metric. We tried to use a balanced number of positive follow-up utterances and negative follow-up utterances. So in the end, after all multiplication, we have 16 positive follow-up utterances and 16 negative follow-up utterances for a grand total of 32. Okay, so how does this link back to our dialog breakdown? What we can do is that since we already have a k-mean that we trained earlier, we can actually compute the embedding of these follow-up utterances and then put them into their designated clusters. So the example over here, I have assigned some random numbers. So the blue numbers are the original speakers, and the green numbers are the positive utterances, positive follow-up utterances, and the red one are the negative follow-up utterances. So what we can do is that we can compute the bigram and trigram cluster probability from the training data. So if a probability of a trigram cluster going into the negative clusters are more than the positive cluster, then we have a breakdown. So we are going to evaluate this approach on two datasets. So the first one is dialog breakdown detection tree, and another one is word chat. So it's a relatively simple dataset. Basically, we have a pair of speakers, and then it's manually annotated with either breakdown label or validity label. So we simply take the highest label. So since 12 is higher than it's not breakdown. So this is our result. The baseline for DBDC3 reported in the paper was around 0.3 accuracy and 0.37 F1 score. So we can see that across all cluster numbers, the accuracy is pretty good. And for the F1 at the optimal cluster number is 0.6, which is quite a significant improvement. What's interesting is that even though BERT is not pre-trained on dialog data like dialog GPT, it actually performs better at the optimal number of clusters. This could be due to the fact that BERT is an encoder and hence is able to produce embedding with better thematic content compared to a decoder like dialog GPT. This is why it would be interesting to compare with other encoders like Roberta or other decoders like the original GPT-2 or even the new GPT-3 if we have it. Okay, so lessons learned. We learned that we are able to represent dialogue as a dynamic phenomenon over a thematic basis. We are also able to use clustering and turn transition probability to predict dialogue breakdown. Future work include comparison with other models and other ablation studies. We also want to compute correlation with annotation, especially with a new batch of annotation ongoing currently at ANT. And we also want to further explore thematic-based clustering properties. So that's all from me. I'll take any questions now.